So as for the great challenge project of the Xin Center, I think one of our young faculty member, Jie Bao, have given the presentation. So his project is really a challenge in the field of the nanophotonics. To support his project, I would like to introduce other research results in our department on this field and show how the nanophotonics is opening up a new world. So we know nanotechnology. What is nanophotonics? It's no doubt we know that our world today cannot do without electricity, but maybe you haven't realized photonics, optoelectronics have already very, very important to our society and human lives. From the area of information, such as communication, storage, display, sensor, to the fabrication, energy, solar cell, all the medicine. So all the optoelectronics devices based on the interaction between matter and light. So nanophotonics is to control the material structure and its interaction in nanoscale. We can design the nanostructure to control the behavior of the electron and the interaction between the electron and the light. Even we can control phonon. Phonon is a kind of mechanical vibration. It's very sensitive to the nanostructure. So nanophotonics create a lot of novel optoelectronic effects. So what's new? What's new in nanophotonics? Here I want to show you 3 examples. We know light has the faster speed in the world. So nanostructure can slow down its speed. We know metal cannot transmit light. But in nanostructure, metal can transmit light and even can enhance the field in the surface of the metal surface. So can you imagine light have force to pick up and move objects? Of course, it's very weak, so we cannot feel it. But it's maybe an only approach to manipulate the living cell, because it's very gentle, very soft, and can soft enough ensure the living cell not to be hurt. So next I will show you the detail of these 3 examples. Control speed of light is very amazing thing. We can reduce the speed of light to only 1 of several hundreds. Here show you the simulation results for nanostructure, the optical waveguide with different nanostructures. So you can see we can get the different speed of light in different channels. So slow down the speed, light can interact with the electron in a very, very small space. So it makes us impossible to develop ultra-compact optical devices. Our lab developed a kind of very ultra-compact optical switches by using the slow light effect. The size is only 10 micrometers and the bandwidth is larger than 24 nanometer and the exchange ratio larger than 15 dB. So the typical size of the optical switch is 10 milli. So using the slow light effect, we shrink the size of the device 1,000 times smaller in one dimension. So that means 1 billion in its volume. So what's the meaning of 1 billion? That means we shrink a building with a height of 45 meters to 45 milli solar cells. So we can realize photonic integrated circuit. We call it PIC using such compact, ultra-compact optical devices. So PIC, we know IC. We know how IC changed human society. From the first computer to the CPU chip today. So we can, this is a very big progress. We can imagine the same progress can realized by photonic integrated circuit. We can integrate a very complex optical equipment into a very small chip. In our lab, we can make a lot of size of the shape of nanostructure. So we can realize not only the switch, but also other optical devices, such as light source or detector. Light source in nanoscale, we call it a nano laser. So maybe we can make it possible to implant the nano laser deep inside your brain to institute to stimulate the bone-mid neuron. So for detector in very small nanoscale, maybe we can make it possible to make a chip of prosthesis. So you can see just one novel effect, slow light, we can realize a lot of innovation, make impossible come true. So next I will show you what's happened to the photon force application. Photon force application in the so photon force, I think it's very interesting. It's a kind of radiation pressure. So if you doing an experiment here, you can very slight deformation or vibration you can observe when a light attached to the plane. So if a light with a vortex beam, so you can use it as a spanner. This kind of spanner can manipulate a particle or unzip the DNA ellipse. So it's very useful. Unfortunately, up to now, the vortex beam can be obtained, only can be obtained by very complex setup. So in our lab, we proposed and developed a kind of vortex beam emitter chip here. So the structure show you here, composed with some gratings or the nanowire curves, nanostructure. So when we import light from this end, we can get a vortex beam in this direction, in this vertical direction. So here show you the simulation results. So based on this structure, we can realize integrated multi-functions on a single chip, such as manipulation, imaging, detecting, and so on. So this experiment is, and the fabrication and the measurement is undergoing now. So next, I'd like to show you the metal photonics. We know silicon photonics. Do you know metal photonics? Metal can transmit light when in the when in a very thin nanofilm. Metal nanofilm can transmit the light, and nanoparticle can localize the light. So both of them are in the surface, very special surface mode. So we call it a surface plasmon polariton, SPP. Because it's a surface mode, so it's very sensitive to the surrounding. So we developed a very unique structure, realized a molecule sensor here. This kind of sensor can sense very thin layer, even thinner than 10 nanometers, 7 nanometers. So single molecule layer can be detected using this structure. So based on this structure, we developed a kind of portable sensor of Bisphenol A. Bisphenol A can code BPA. This is a material commonly used in the production of the plastics. It's a kind of environment contaminant. So to maybe this kind of material exists in the bottled water. This is the structure of our sensor. This is the sensor surface here. And after growing the antibody here, we can catch the molecule, the BPA molecule in the solution. So the safety standard, the minimum detectable concentration of BPA solution is 0.1 nanogram per milli. So the safety standards for the BPA in European Union is 10 times larger than our measurement data. So we take some productions of the bottled water in the market and do the experiment. Yeah, I cannot tell you the brand. They are very different data can obtained by this sensor. So here, if these results also published last year, and if we change the antibody here, we can get the other material. We can sense the other material using the same structure, such as gas, alcohol, or melamine here. So this is a nanofilm. As for the nanoparticle can localize the field, the light field here. So sometimes used in the solar cell to improve the absorption of the light here. So in our lab, we developed a kind of co-share structure here. The co-share structure not only can localize the field to improve the absorption here, but also they can to isolate the metal and the electron and the hole, so improve the efficiency of the solar cell. This is a nanoparticle structure fabricated in our lab. You can see very uniform and compact shell structure, very, very thin as 2 nanometers is formed. Based on its structure, we proposed and fabricated a pump-cone structure. Pump-cone alloy nanoparticle. The nickname is PAN, not panda, PAN. Yeah, this kind of structure have a lot of very fine structure. So he have characteristics for broadband trapping light. We do the experimental by putting PAN into the dye solar cell. So improve the efficiency very significantly from 5.3% to 7.9%, nearly 30% enhancement was observed here. So we can design a commercial model for this kind of technology. Maybe we can make a PAN solution. Maybe, yeah, this kind of PAN solution as a product. We provide PAN solution to the solar cell maker, and yeah, it's better for us to demonstrate this kind of PAN not only effective for the dye solar cell, but also for other type of solar cell, such as silicon solar cell or the organic solar cell. Of course, we have to give a solution to how to mix the PAN solution into the fabrication process for the solar cell. Of course, using other material, we can make a lot of other kind of nanoparticle, such as reported by the Jiebao, the quantum dot. The restless nanoparticles also have the same function. So the nanoparticle also very, very very important role in the nanophotonics. So in summary, the results of the nanoparticle, nanophotonics, I think is not very, is immortal here. Maybe it's need incubated, but it's very important and show us the potential to change the human society and maybe have a lot of innovation opportunities. So we hope Xin Center can create a very good environment for the development of the nanophotonics here. So, okay, thank you very much for your attention.
So is this vortex beam emitter? In the vortex beam
Yeah.
Can you control the charge and the direction? Can you have different?
Yes, they have the different order. Here,
Control it electronically?
Yeah, the volume? You mean the size of the volume?
The number of turns you have the charge.
Yes, the charge, we can get charge from, yeah, of course, zero charge is plane, so -1, +1 to the very high order. We can design, it depends on the ring structure. If we have 4, we can get 4, -4, and +4. If we can fabricate 40, we can get a very, very complex vortex beam here.
Then I have another question related to this. So how focused it can be? I mean, basically this vortex structure, how small it could be?
Mm-hmm. Yeah, because this structure is very small, smaller than 1 milli. Yeah, the whole structure is smaller than 1 milli, and this area only 10 micron. So we needn't focus it.
It's a question quite related to what Professor Diarrier asked. Can you make, I understand you can design all kinds of vortices, but can you design a complex that will make dynamic changes? Namely that by 2 or more inputs, you will change the order of the vertex, or change its position, or things like that.
Yeah,
Dynamic
yeah.
control vortices.
Yeah, it's a very good question. Recently, we started the research on the OAM beam for the communication. So we have a structure designed to encode and decode this kind of OAM. So we can change the structure here and to control the coupling of the curve and the grating to change the charge and even the direction. It's possible.
Okay, thank you.
Thank you.